In this class, we deal with extrinsic semiconductors. In the previous class, we have already known about intrinsic semiconductors, and we have studied that the conductivity of an intrinsic semiconductor depends on temperature. So, at room temperature, we cannot expect a high conductivity for an intrinsic semiconductor. So, in order to enhance the conductivity of an intrinsic semiconductor, we have to use a method called doping so that we can enhance the conductivity. Such a semiconductor produced is called an such a semiconductor produced is called an extrinsic semiconductor. So, the total picture is like this: intrinsic semiconductor on doping. So, this is the process of adding some impurity to an intrinsic semiconductor. Impurity doesn't mean it's not in its normal sense. Impurity means any other atom other than the atom of an intrinsic semiconductor. So, an intrinsic semiconductor on doping, we can convert it into an extrinsic semiconductor. So, what are we doing using this doping? It is actually to enhance the conductivity of an intrinsic semiconductor over a range of temperatures. So, doping is the process of adding impurities to an intrinsic semiconductor to enhance its conductivity. Doping can be done in two ways: either by adding a pentavalent impurity or by adding a trivalent impurity. The impurity added during the doping process is what is meant by dopants. So, for a pentavalent impurity, the dopants can be arsenic, antimony and phosphorus. So, when I write it, arsenic, we can add antimony and phosphorus. So, pentavalent means valency 5. And for trivalent impurity, examples are indium, gallium, etc. So, by doping a pentavalent impurity, we are creating one type of an extrinsic semiconductor, which we call as an N-type semiconductor, and by doping a trivalent impurity, we are creating another set of semiconductors, which is called a P-type semiconductor. So, the type of extrinsic semiconductors are N-type semiconductor and P-type semiconductor. So, now we will deal how an N-type semiconductor is produced. N-type semiconductor is produced by adding a pentavalent dopant to the silicon crystal. So, let us study about it. N-type semiconductor. So, we know that the silicon crystal, it is having an atomic core which is bonded to the other neighboring silicon atoms. The silicon cores are shown by +4, and they are all a never-ending structure created. Like that it continues. So what happens? When we add a pentavalent impurity, what will happen? When a pentavalent impurity is added, this pentavalent impurity will take the place of silicon, displacing it. So what happens is that a pentavalent impurity will come here. So what happens is that it has 5 electrons in its valence shell. So 4 of the electrons are getting bonded with the adjacent silicon atom. So what happens to the extra electron? It is freed into the lattice. So this pentavalent atom is having 5 electrons and 4 is used for bonding and 1 is freed into the solid structure. So what happens is that this happens at many sites in the crystal. So that in an intrinsic semiconductor, we know that Ne was equal to NH. The number of electrons was equal to the number of holes. But in this case, as an extra electron is given out by a pentavalent impurity, and this happens at many sites in the crystal, inside an N-type semiconductor, the number of electrons will become equal to number of holes. This equation was satisfied by temperature generated carriers. They are called thermally generated carriers. Ne is equal to NH. So before doping, the electrons and holes were there since the temperature was greater than 0 Kelvin. But this was disturbed by these additional electrons given by this N-type impurity coming. So it will become Ne greater than NH. So this type of semiconductor where the negatively charged electrons are the majority carriers and the holes are the minority carriers. Electrons are more in number. That's why they are called the majority carriers and holes are called the minority carriers. So once again, an N-type semiconductor is a semiconductor in which the number of electrons is greater than number of holes, or electrons are the majority carriers and holes are the minority carriers. So what is the name given to this particular atom coming here, pentavalent? It is donating an electron to the crystal structure. So this pentavalent impurity is called a donor. The pentavalent impurity is called a donor. You have to understand it. Now we will deal with a p-type semiconductor. How is a p-type semiconductor produced? We know that by doping an intrinsic semiconductor with a trivalent impurity, we can change it to a p-type semiconductor. So once again, we are going to the crystal structure of silicon. So we have already drawn the crystal structure of silicon. So you have to understand it just like a cinema. What is going to happen here? You may be already anticipating what is happening. So there is a never-ending structure of silicon. To that place, we are doping a trivalent impurity. So trivalent impurity, when it comes here, it has only 3 electrons in its outermost shell. So these 3 electrons get bonded here, here and here. And there is no electron to get bonded here. So here there is a vacancy created. So by adding an impurity, a trivalent impurity, a vacancy is created in the bonds. What is the vacancy of an electron called? Hole. So what is the effect of adding a trivalent impurity? More holes are produced. This process happens at many sites in the crystal so that the Ne is equal to NH condition of the thermally generated charge carriers is disturbed, where the number of holes here, the extra added holes, become greater than the number of electrons. So in a semiconductor in which the positive holes are the majority carriers are called a p-type semiconductor. So what happens is that, do you think that this hole will remain here forever? No. Most electrons are there, right? So what happens is that some electrons may move from, one electron may move from some of the sides to this hole to fill this. But as an effect, another hole is produced there. So when an electron is moving, holes are generated. So holes will be moving, electrons will be moving, and they will be contributing to general conduction. But here you have to note that the number of holes are the majority carriers, electrons are the minority carriers. Number of holes has become more than the number of electrons. Here, to sustain the bond, this atom has taken an electron from somewhere. Not at the instance when doping has happened, but after some time it may take an electron somewhere from the lattice. So this type of a trivalent impurity is called an acceptor because it accepts an electron from some other site. Hope you have understood it well. Thank you.